Hello and welcome to Eng Phys 2P04 Lecture 20, General Elasticity. So the previous analysis we've been using where we said that G was equal to E over 2, 1 plus nu, and all we needed to know was the Young's modulus and the Poisson's ratio to characterize the material, is only applicable to isotropic materials. We mentioned that a bunch of times throughout, and now we're going to explain how to deal with non-isotropic materials. There's three different levels of anisotropy or non-isotropicness that we're going to be looking at, where a material is basically the same, but it just doesn't obey G is E over 2, 1 plus nu, so we just have to know, we have to be told the shear modulus separately. One where we can have a different Young's modulus, Poisson's ratio, or shear modulus in different directions, x, y, and z, so this has a different stiffness in x than it does in y. And then we can use very similar equations. We'll just need to have different numbers for those different axes. And then the most anisotropic case we're going to deal with, which means we're going to need to use the general elasticity equations, are cases where we have axial and shear stress coupled together. This is the case for something like quartz. So looking at the general equation then, in general we'll have to say that stress in any of the dimensions depends on the strain in any of the dimensions through the stiffness in any of the, that couples the strain in any dimension to the stress in that dimension. So this is a double sum,Cijkl, epsilon kl, going to sigma ij. Try writing it out to make sure that you know what it means. Pick one and say something like sigma 2, 3, and then trace this through and see what the sum gives you. And you'll see that sigma 2, 3 is going to depend on all of the different epsilons, all the way from 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, all the way up to 3, 1, 3, 3, 3, epsilon 3, 3. And there's a different coefficient for each one of those. So in total, there's 9 different C's. C is the elasticity on the I face in the J direction in response to strains on the K face in the L direction. SoCijkl maps strains on the K face in the L direction to stresses on the I face in the J direction. So we wrote the subscripts as numbers, but 1s mean X, 2s mean Y, 3s mean Z. And oftentimes we're going to be writing out the letters rather than the numbers. This is usually the case for the stresses and strains, but not so much for the coefficient mapping them. So we'll almost always use numbers for this mapping coefficient, but we'll use letters sometimes for the stress and strain. Whenever you've got double sums like this, or a lot of sums, then it's useful to use a shorthand called Einstein summation notation. Here we define sigma ij, c ijkl, epsilon kl to mean the version with the sums. So the key is the repeated indices. See how we've got this kl multiplied by this other term kl? That means we're going to be, since there's a k in this term and a k in this term, but no k on the left, then what this means is we're implying a sum over all of the k's. And same thing for L. So here's a couple of examples in Einstein summation notation. You can use this notation if you want. I'm not going to use it all that often. I'm just presenting it here so that if you go and look up something on statics and see this, something like this written with repeated indices in different terms, then you understand that there's an implied sum. So this is my due diligence to explain Einstein summation to you, so you're well equipped to do that. You can use it though. If you feel like using Einstein summation, then myself and the TAs will know what you mean. So there's an example using Einstein summation here. Try and write these sums in Einstein summation, Aij, Bj. Well, you just don't have to write the sum. It's already there. So Aij, Bj. And then the total derivative. So here's an example of, you've seen this in second year math. In first year math, df is partial of f with respect to x times dx, etc. And the trick is to use x1 for x, x2 for y, and x3 for z. Then this just becomes del f by del xi dxi, or without the sum in Einstein notation. All right, tensors. So a vector is a one-dimensional array of numbers, and a matrix is a two-dimensional array of numbers. In general, the most a mapping of a one-dimensional array of numbers, a vector, to another one-dimensional array of numbers requires a two-dimensional array of numbers, because every entry over here can depend on every other entry over here. So we need three numbers, in this case A1, A11, A12, A13, to map these numbers over here. And if we can have a different dependency for Y2, then we need three different numbers to map these ones to these ones. So to map X, X1, X2, X3 to Y2, and a different set of three numbers to map the X's to Y3. So the way to say this is under tensor language, is that a vector is a rank 1 tensor. You refer to the dimension of the array of numbers. A matrix is a rank 2 tensor. And to explain this idea that you need a matrix to map one vector to another in the most general linear mapping, you'd say that the most general linear mapping of a rank 1 tensor to a rank 1 tensor is a rank 2 tensor. All right, well, the stress and strain terms that we're looking at now, we've got, they're a two-dimensional array of numbers, right? We've got xx, xy, xz, yx, yy, yz, zx, zy, zz being mapped from strain to stress. So thisCijkl is a rank 4 tensor. We've got a rank 2 tensor mapping to a rank 2 tensor. So the most general mapping is a rank 4 tensor. Now we can't really write that out in 2 dimensions here, and it's pretty hard to visualize too, because this is actually, you can think of it like a matrix, except instead of being a 3 by 3 matrix, it's a 3 by 3 by 3 by 3 matrix. So it's a 4-dimensional elasticity tensor. Okay, that's kind of complicated. Fortunately, there's a way to avoid doing that altogether. And that way is Voigt notation. So in Voigt notation, what we do is, instead of writing this as a matrix, we're going to write it as a 9 by 1 vector. So just imagine taking all these elements and writing it all out. So there's 9 of them, and then these elements. So there's 9 of them, and now we've got, instead of a 3 by 3 by 3 by 3 matrix mapping this to this, we've got just or a 3 by 3 by 3 by 3 rank 4 tensor. We've got a 9 by 9 rank 2 tensor. So it's just going to be a matrix mapping from one to the other one, and that we can write out in 2 dimensions. In fact, we don't really need to write out a 9 by 9 and to write out all components of this, because since the shear terms are symmetric from the work that we did in the last section, we know that epsilon xy is always going to be equal to epsilon yx, and same thing for the stresses. Sigma xy is equal to sigma yx, at least locally. So because of that, we can get away with skipping the last 3 components and just write out a 6 by 6 matrix to map 6 components to 6 other ones. Okay, a couple of comments about this. First 3 entries are the axial ones, the normal, stress, and strain. The final 3 are the shear. Notice that we've doubled up on the shear term, so we've changed from 1 times the shear term to 2 times the shear term. So in other words, this is now, up here we had true shear strain, and now we've got 2 times true shear strain, which you know is engineering shear strain. So if you want, you can just replace these 2 epsilons with gammas for the last 3 components. Another comment is the ordering of the elements. So we go x, y, z. That's not surprising. Then we go y, z, x, z, x, y. What's the pattern for this? Well, these are the ones perpendicular to a certain axis. So perpendicular to the x-axis, we've got the coupling between y and z. Perpendicular to the y-axis, we've got xz, and to the y-axis, to the z-axis rather, we've got x, y. So this is, we go x, y, z, and then not x, not y, not z. Right. Now, why did the 2's show up? If you multiply this through, so sigma xx, multiplying through, you have the 2's showing up there, and then because yz, xz, and xy shear strains are equal to 2 times those, you can re-express as just epsilon 2, 3 plus epsilon 3, 2, since the transverse shear terms are equal. So the corresponding shear terms are equal. So here we've done that. We've written this out as 1132 and then epsilon 23 plus epsilon 32, and then doing the same thing for this term and this term. And now examining this sum, you can see that it works out to the same thing we had before, where sigma 11 is equal to sigma 11 KL times epsilon KL. There's some Einstein summation for you again. Now, void notation is all anybody uses when they're dealing with stress and strain. Well, maybe some people use the full tensor notation, but we're definitely not going to use that. We're going to be using void notation all the time. So because of that, you'll see these coefficients often not defined as their rank 4 tensor coefficients, where we've got 4 subscripts, but instead we refer to them by just 2 indices, by where they show up in this matrix. So it's a little bit tricky to remember where what coefficient goes where. So C1213 is actually the 6,5 entry, but how do you really get that? Well, you can think about it. It's not really too bad if you think about what it's mapping from what to what. So C1213 being where it is in the matrix, it's got to map the XZ, the 1,3 shear strain rather, to the 1,2, the XY shear stress, right? So sigma XY is going to depend on sigma epsilon XZ in a way that corresponding to coefficient C1213. Okay, so there is some logic to this, but to avoid having to rethink that out every time you use it, most people just use the 2 and X notations. And now Hooke's law would just read this using our capital C for the stiffness matrix. Not necessarily, well, it's still a rank 2 tensor, but we're just going to refer to this as a stiffness matrix rather than the rank 4 stiffness tensor. And one last point. So we mentioned this already, that true shear strain is half of the engineering shear strain. So really the void notation, even though, and in fact, because we used true shear strain in the tensor definition, because of the dropping of the subscripts and this doubling that needs to show up to have the equation work out the same as before, the void notation has to use engineering shear strain. You can also use, you can write out a compliance matrix just like before. The compliance matrix is the inverse of the stiffness matrix. All right, so example isotropic stiffness matrix. Whenever you get told a general equation for something that you were using a simpler equation for earlier, it's a good idea to see how your previous understanding fits into this new general equation. So that's what we're going to do here. We're going to take our isotropic material Hooke's law that we know and try to figure out what the compliance, what the stiffness matrix would be in void notation. All right, well, the axial ones map to the axial ones, and the shear ones map to the shear ones. It's kind of like 2 independent 3x3s with zeros on the kind of diagonally sections. So then, substituting in the numbers that we know for these mappings, we come up with this, and that's it. So this is kind of just combining all of the axial and shear things into one matrix mapping. All right, well, we can do the same thing for the compliance matrix. Compliance matrix, we could just invert this, or we could rederive the same kind of logic as we did, using the same approach as we did to get this, and let's do that. So that should be your answer. All right, well, if we're only going to ever deal with isotropic materials, this is a lot of a waste of time and computational effort. We don't need to write out this coupling because it's just 0 over there, and the shear and axial terms aren't coupled together. However, consider the compliance matrix for quartz. Look at this. Okay, so notice a couple of things. Notice, one, the Z, Young's modulus is now different than the X and Y Young's modulus. So we've got the these are sort of like the inverse of Young's modulus on the diagonal here, you remember, for the compliance matrix. And so you can't really say the Young's modulus for quartz because it depends on which direction you're talking about. And maybe more interesting, we've got components here. What do these do? Well, these components in the compliance matrix map so this one here transfers shear stress in the YZ direction into axial strain in the X direction. And this one transfers shear stress in the XZ direction to axial strain in the Y direction. Whoa. So what this means is if you kind of fold a quartz crystal into a diamond, you like compress it along the axial direction, you shear deform it, then it's going to change size and shape on the transverse direction to that. So that's on the perpendicular, like the longitudinal direction. That's kind of interesting. And similarly, we've got some more weird coupling over here. So this means that the shear strains are actually, the shear stresses and shear strains are coupled from one axis to the next. A lot of materials fall somewhere in between being purely isotropic and as anisotropic as quartz is. So this is an example of one example is an orthotropic material, which has the same components as isotropic, except that the relations on different axes can be different. Usually this happens because the z-axis behaves differently than x and y. So x and y are treated the same for this matrix, but z is treated differently. So you see that we've got the perpendicular to x, perpendicular to y shear terms are the same, but the z one's different, and then x and y Young's moduli behave the same, but the in z it's different. So here's some examples of this. Any kind of hexagonal close packed crystal is going to be this crystal class, is going to have this symmetry, transverse isotropy, transversely orthotropic rather. So here's some examples. Common material, titanium, magnesium, cobalt, all have this this setup, and I've copied in some coefficients for you. Do you have to memorize these? No, of course not. That would be silly. You've got a table here if you need them though. Okay, and then a little bit more symmetric is a cubic crystal material. So this is these are hexagonal. They're not really cubic, but they still behave the same in x and y, just differently in z. Now these materials behave the same in x, y, and z, but in general don't have the shear modulus relating to the Young's modulus and Poisson ratio the way that we have for an isotropic material. So here's a big list of crystal materials here which have this this setup. So these are they're not truly isotropic, but they do still have the same isotropic set of parameters. And if you were to just look at this at the axial stress or the shear stress, then you might conclude that they're isotropic. But if you compare how the shear modulus is determined to our equation for isotropic materials, then you'll find that it behaves a little differently. But you could analyze these the same as we did for isotropic materials, just with a different shear modulus. Now we've got a new parameter here, A. A is just telling you the degree of this anisotropy. So A is defined as the shear modulus divided by what the shear modulus would be from that Young's modulus and Poisson ratio for an isotropic material. So if A is bigger than 1, it means it's more resistant to shear. It's got a bigger shear stiffness, G. But if A is less than 1, then it means it's less resistant to shear. It's got a lower shear stiffness than what you would think it would have based on its Young's modulus and Poisson ratio. So we can look across here, look for some materials that are it's always interesting to look for some extreme materials here. The lowest one I see in this table is, whoops, messing with the table, is 0.36. And 0.36 is calcium chloride. So this material is easy to shear compared to how easy it is to deform axially. And a large number in this table, 9.95, this is sodium, quite a lot more difficult to shear than it is to deform axially. Okay, for the examples, what I'm going to be doing is kind of getting you started on what you would need to have done so that you can use general elasticity for the sample problems. So first one is void notation in FlexPDE. Modify one of your FlexPDE scripts from lecture 19 to use void notation to couple shear to axial stress and strain. So if we use the same numbers as we did in lecture 19, where it's an isotropic material, then doing this should not actually change the results we get for the script. And this is a good test that you've written in the void notation correctly. So using the beam extension code, for instance, the extending beam example that we were doing, the C11s behave, and 2233 behave the same as before, 12 same as before. Now we need to define up to 4, 5, and 6 coefficients. Since this is an isotropic material, those are all 0, but we'll enter the variables anyway. And 4, 4, 5, 5, 5, 6 are just the shear modulus. Then, etc. for the off-axis components for shear, that none of those are true. And then it's a good idea, it'll probably be a time saver since all of the ones we're going to be dealing with are symmetric matrices. Then you can enter the lower half of the matrix, so the lower triangle, everything below the main diagonal down here, just to assert the symmetry. And then when you're entering a new material system, you just need to mess with the ones up here. Good to only type in any one number once. So here I'll type in the Young's modulus in the 1, 1 direction, and then I'm not going to copy and paste this even for 2, 2, and 3, 3. I'll just assert that it's the same as it was in 1, 1. This way you only have to enter each number once, and if you go back later and you decide, oh, I'm going to change this relationship, then you know that it's going to be changed in the other axes accordingly. So you can't, you won't screw it up as easily that way. Next, the engineering shear strain is what we're using for these coefficients. So these map to engineering shear strain. We'll just get rid of the divided by 2 there. And then we just write out Hooke's law using the 6 by 6 matrix multiplication result. So stress equals the C matrix times the strain, x, y, z, perpendicular to x to y and to z. And then if you run the code, you'll see that it still works. This would work either for the pure shear cube or the beam extension code, whichever one you like, or any of the ones that you did in the assignments. Okay, last thing we're going to do is the quartz stiffness matrix. So we had the compliance matrix for quartz, but our FlexPDE code needs the stiffness matrix components. There's a couple of things we could do here. We could either try to rewrite the code to deal with compliance rather than stiffness. That's a lot of work. So instead of doing that, what we're going to do is just use Maple to find the stiffness matrix. All we need to do is take the inverse of this. Give that a shot. Okay, so here's the code for doing this. If you're writing out a matrix in Maple, it'll probably be easier to see the components if you use line breaks. Again, you can do Shift-Enter to do this. And there's our inverse. So that's the stiffness matrix for quartz. Here you'll notice that there's a couple of e to the minus 18 terms and e to the minus 19 terms. Those are really 0. This is Maple running into like a rounding error. Computers have a hard time dealing with really small numbers, especially since we entered this in terms of decimals. They weren't, the coefficients aren't exactly 12.77 and 20.04. Last thing to mention is this was in picometers per meter Pascal, which is like e to the minus 12 per Pascal. So what are the units of C if we took an inverse of this? E to the minus 12 per Pascal. Well, the units of C should be pascals divided by e to the minus 12, or in other words, pascals times e to the positive 12. And by e, I mean like 10 to the positive 12. So in other words, this is in terapascals. Okay, you get to use these coefficients in the assignment, so I'm just going to jump over to the sample assignment for this lecture, for lecture 20. This is what we've got. So here we're going to explore how quartz behaves. We're going to apply an X tensile stress on one of the faces, just like we were doing in lecture 19 to find out the the extension of the cube. So this is a pretty severe one. We're not going to apply quite as much as this because the cube gets too deformed if we apply a stress that's equal to the Young's modulus. The Young's modulus, so the stress is actually 10 gigapascals rather than 1 gigapascal like it was last lecture, but now we're going to be, because quartz's Young's modulus is a fair bit higher, this is effectively a lower relative stress. Now the quartz would actually break if you gave it this kind of tensile strain. So this is a huge amount of strain for quartz. It's on the order of 100 times bigger than you would ever want to be putting onto quartz. So this is quite a lot of strain, and it can't actually deal with this. It's better in compression than it is in tension. So just as an academic exercise anyway, let's see how it would deform if we were to apply this. We want to apply this big stress to see be able to see the deformations. Now I'm just going to point out one thing, which is the fact that this crystal anisotropy leads to some pretty interesting shapes. So here what's happened is we haven't applied any forces on the sides or the top and bottom. All we've done is pulled this out of the page, so in the positive x direction, which is the out of the page direction. And then because of all that shear anisotropy that's going on, the crystal deforms. It tries to form itself into a diamond. We get a YZ shear showing up as we pull on the crystal in the x direction. Isn't that great? Think of all the neat applications you could have in that sort of a material system. We'll see next week that quartz actually also couples its electric fields to its stress fields, so you can do some even more interesting things.